The first thing we need for a robot to follow a route is for the robot to know where it is. It is usually very complicated. Fortunately, Cyan has got you covered with integrated localization systems. But first, a quick rundown on how they work is necessary. This assuming we are using a differential driving base. The first thing we do is we get the displacement of each wheel. Then we take the average of that. After that, we need some way to get the heading, either through an external sensor or through internal calculations. After that, we multiply the average displacement by the sine tangent of the heading of the robot in order to calculate the position of the robot in the y-axis and the cosine tangent of the heading of the robot in order to calculate the position of the robot in the x-axis. Don't have an external heading sensor like the IMU. We just use kinematic equations and a constant, the track width, the distance between the centers of the two wheels, in order to calculate the heading. And we're pretty much done. So let's get to the actual implementation of it. So the first thing we need is two motors. After that, we're going to need a very important constant. It's going to be of type double and it's going to be Tx to linear distance. Now, what does this constant represent? So our encoder doesn't actually measure the distance in centimeters. It measures rotation in its own unit called ticks. The relation between a tick and the full rotation is different for every encoder. So for your encoder, just look up the CPR. For example, for the rev core hex motor is 28. So let's use that. And we divide, but by what do we divide? So it's going to be 2 times pi math.pi times the wheel radius. In this case, it's just going to be 4.5 because I guess we're using 9 centimeters wheel. By the way, the same thing applies to inches. So why do we do this equation? Well, right now we have calculated the rotations that our motor has done, which is pretty much useless unless we can convert it to linear distance. So we just multiply it by the circumference of our wheel in order to get the total displacement. Now, don't forget to initialize the motors. And now let's get to the fun part. First of all, you're going to need the localization system. So in this case, we're going to use the tank kinematics. And for this case, we're going to name it tank kinematics. But again, you can label it whatever you want. Now, let's initialize the tank kinematics. To do that, we're going to need a measurement provider. What is that? It's a helper object that points to where the system needs to get its measurements from. So let's just say measurement provider and let's see what it takes as parameters. If we pick inside the constructor, as we can see, it takes two double suppliers. Basically, is for the left encoder. So I'm going to do get position, right encoder, get current position, and the constant we created earlier. So let's just put in that too. And we're basically done with the measurement provider. So let's move on to the main, I would say, thing. Since we're not using an IMU for this example, we're gonna need just another constant, which this constant is the track width. If I can spell it correctly, yes. Now, this will depend on the base of the robot. But one important thing you should not overlook, in order for this to work correctly, the wheel radius and the track width should be in the same distance unit. Centimeters, centimeters, inches, inches. Alright, now let's initialize the tank kinematics object finally. Now, what else did it take as a parameter? As you can see, it takes the initial heading, the track width, the constant we created earlier, and the tank kinematics measurement provider, that object. Yeah, that object. The external heading of 0, and give it the track width and the measurement provider, and we're pretty much done. That's it. Now, if we want to display the position, I guess, the rotation, and we can do tank kinematics dot get pose dot get y, and the same for x. Now, the whole program runs in an update loop. So where do we actually update? Remember why we created this object? Well, this object points to these two motors. So we can update it whenever we want to, whenever it is needed. So we are not going to have to worry about that. Now, what if we actually use a gyroscope, an IMU, an external sensor? Well, in that case, we are going to use the gyrotank odometry. First of all, we get rid of the track width, since we don't really need this, and we're going to get rid of the here too. So, first of all, we're going to give the measurement provider the pointer, the MU reading. So, it's going to be .get yaw pitch dot angles and get yaw. Now, let's convert the constructor here too. I almost forgot, and we're pretty much set. This has been another tutorial. Thank you for watching and καλή συνέχεια.